Okay, so for page 70 of your interactive notebook, you're going to label it Properties of Exponents. And then that little mini book that I had you make is going to go at the left-hand side of that. And then we're going to take these properties that you learned in Algebra 1 and we're going to apply them. But we're going to apply them to rational exponents now. What I mean by that is exponents that have fractions in the exponent. Okay, so our first example, we're going to do about 10 of these. The directions are to simplify the expressions. So our first example is 7 to the 1/2 times 7 to the 1/4. Now, you have a rule in your book of property exponents that says if the base of the exponential expression has the same base, if it's the same, you can simply take those exponents and add them. So this would be the same thing as rewriting the 7 one time and adding the 1/4 plus 1/2. When you do that, you get a common denominator. 1/2 turns into 2/4, so you get 7 to the 3/4. You could submit it as this, or you can rewrite it using your rules of radicals. The 4 in the denominator becomes the index, and the 3 remains as the exponent on the 7. Now you could go ahead and figure out what 7 cubed is. It's 343, so you could also rewrite this as the 4th root of 343. Now you wouldn't be able to do anything with that because 343 doesn't have a perfect 4th root. So this would be the end of the problem to simplify it. For number 2, here's your next problem that you'll simplify. You've got 6 to the 1/2 times 4 to the 1/3 squared. Alright, you have a rule in your book that says if you have the product of two expressions being raised to a power, that power can be distributed to each of them separately. So for example, I can give that square to the 6 to the 1/2, and I can also give it to the 4 to the 1/3. I would now multiply those two. You have another rule that says when you have a power raised to another power, you multiply the two numbers. So 1/2 times 2 is 1, so you have 6 times 1/3 times 2 is 2/3. So we're going to rewrite that 4 to the 2/3 using its radical form. The 3 becomes the index on the radical, and the 4 would be squared, but I rewrote that as 16. Now, even though 16 itself is not a perfect cube, it actually does have a perfect cubed inside. That perfect cubed is 8. So, if you were to separate 16 into 8 times 2, you could take the cube root of 8, which is 2, and you would multiply that 2 by 6 to get 12. So this would turn into 12 cube root of 2. Your next example is very similar. The only difference is you have a negative in your exponent now that you're raising it to. But as far as start the problem off, you would start it the exact same way we started number 2. So you're going to distribute. Oh, I did not do it that same way. The reason this one's just a little teensy bit different is that if you notice these exponents, the 1/2 and the 1/3 were different. These exponents happen to be the same thing. It's a 5 and a 5. So what I'm going to do is I'm going to actually multiply the 4 times 3 and then raise that answer to the 5th power. So 4 times 3 is 12. And then now I have 12 to the 5th multiplied by that negative 1/5 and the 5. It's going to give me negative 1. So I end up with 12 to negative 1, and my negative exponent will make the reciprocal of 12 to make this final answer 1/12. For number 4, we have 5 divided by 5 to the 1/3. That 5 actually has a 1 on it, even though you don't see it. And so your rules of exponents say that when you have two expressions that you're dividing them and the bases are the same, you subtract the exponents. This is similar to number 1 where the bases were the same, but instead we added them. But now we're going to subtract them because we're dividing instead of multiplying. So that 1 minus 1/3 is going to be 5 to the 2/3, and rewriting that gives me the cube root of 25. All right. For number 5, we've got 42 to the 1/3 divided by 6 to the 1/3, and all of that is going to be squared. All right, for this one, the 1/3 is going both to the 42 and the 6. So I could actually go ahead and divide 42 by 6 first, and then raise it to the 1/3. So that would look like this. 42 divided by 6 is 7. So now I have 7 to the 1/3 squared. When I multiply these two exponents using my rules, that becomes 7 to the 2/3, which is the same thing as the cube root of 49. All right, for number 6, we've got the cube root of 12 times the cube root of 18. Because these both have the same cube root, you have a rule that says you can multiply the 12 and the 18 together. So when I do that, 12 times 18 is 216, and the cube root of 216 is 6. And then for number 7, we have the 4th root of 80 divided by the 4th root of 5. One of your rules of radicals says that because these two have the same index on the the radical, you can go ahead and make this one big huge radical and rewrite it as 80 divided by 5 with a 4th root on it. And so you would be taking the 4th root of 80 divided by 5. 80 divided by 5 is 16, and the 4th root of 16 is 2. So final answer is 2. Now for number 8, we have the cube root of 64 times y to the 6. One of your rules of radicals says that you can take this cube root and put it on the 64 separately from the y to the 6. So if you have the cube root of 64 times the cube root of y to the 6. Now the cube root of 64 is easy, that's just 4. For the cube root of y to the 6, technically you could rewrite this as y to the 6th power divided by 3. So the answer would be 2, and it would be y squared. Or you can think of this as, what can I multiply 3 times to get me y squared? y to the 6th, and that would also be y squared. So if you use the properties of radicals to turn it into a fraction, it would be 6 divided by 3 to give you y squared, which gives you the same answer. For number 9, we're going to make it a little bit more difficult. It won't be nearly as easy. So we have the 5th root of 4 times a to the 8th, b to the 14th times c to the 5th. These are not perfect 5th roots. There's no 5th root of 4, there's no 5th root of a to the 8, and so forth. However, even though it doesn't have a perfect 5th root, it's not a perfect 5th root, there is one inside of it. So I'm going to split this up using its perfect 5th root and non-perfect 5th root. This is like whenever we have a problem where we try to figure out, let's see if I've got an example like it. Yep. So for example, in number 2, even though cube root of 16 itself was not a perfect cube, it did have a perfect cube inside it. It had 8. So I broke this up into cube root of 8 times 2. And I took the cube root of 8 out and made that a 2. The concept here is the same. So even though a to the 8th is not a perfect 5th root, I don't have a number that I can multiply 5 times to get a to the 8th, it does have one inside. For example, a to the 5th. The 5th root of a to the 5th is a, so I broke it up into pieces. Its 5th root and its non-5th root. And now for b to the 14th, his perfect 5th root would be b to the 10th. Because b to the 10th has a perfect 5th root, and I'm going to split it off of what's left, which in this case would be b to the 4th. There would be 4 left over. The 5th root of b to the 10th is b squared, so that's why I separated it into these two pieces. But b to the 4th doesn't have a perfect 5th root in it. And then finally the last one I can just leave alone. I won't do anything with that one. So now I can use my rules of radicals to now take those pieces out. For example, The fifth root of a to the fifth here is a, so I took that out. The fifth root of b to the 10th is b squared, so that came to the front. And the fifth root of c to the fifth is c, so I took that out. Everything else needs to remain under the radical because they don't have any perfect fifth roots on them. And now for my 10th example, I've got the cube root of x divided by y to the 8th. One of your rules of radicals says that you can give the radical to the top as cube root of x, and the radical at the bottom, which would be cube root of y to the 8th. Now, cube root of x, there's nothing I can do with that one, but y to the 8th at the bottom does have a perfect cubed inside of it, even though y to the 8th is not a perfect cubed itself. So I broke this up into y to the 6th times y squared. That's the same thing as y to the 8th. Y to the 6th is a perfect cube root. So whenever I break this up, the cube root of y to the 6th is y squared, and the cube root of y squared is not anything, so I'm going to leave that one as is. Now, technically, you would have to rationalize this denominator, but I'm not going to make you do that for this lesson. I won't test you or quiz you on that. So technically, you could leave this as a final answer for me because I told you if there's a variable in the denominator, I don't expect you to rationalize it. It is something that you could do. So I'll show you the steps for it. I would multiply both top and bottom by the cube root of y, because the cube root of y times cube root of y squared times y is y cubed. So I would get the cube root of y cubed, which would give me just y to the 1. And so I would have y squared times y, and y cubed would now be in my denominator. But because I had the cube root at the top and the bottom of the fraction, I'm going to do cube root of x times cube root of y, which is cube root of xy. This is the simplified final answer, but as I said, I will accept this answer as your final answer as well. You do not have to rationalize it for me. Okay? And that is all the examples for this page.